time. So what we try to solve is we try to find a propagating mode propagating along x direction at metal dielectric interface. And as I said, in optics, metal is defined as a negative permittivity material, and dielectric is defined as a positive permittivity material. So it's basically you have two materials with one positive, one negative permittivity. You want to find a surface mode that is confined at the interface. So we did that, and then we saw the TE polarization. At TE polarization, there's no surface mode, but in TM polarization, you have surface mode, and this surface mode is called as a surface plasmons. And then here, this is the dispersion relation of surface plasmons. And then if you draw it, it looks like this. As I said, as the omega, the frequency approaches to the surface plasmon frequency, which is defined like this, your K vector tends to diverge. Whereas as omega approaches to 0, then the surface plasmon dispersion relation approaches to the free wave, right? Free space light. So here, another thing that you can notice is that if you think about the slope of this curve, its slope is always lower than the slope of the free wave, which means its group velocity, the group velocity of the surface plasmon, is much smaller than the speed of light. And at the surface plasmon frequency, you can see the group velocity becomes 0, which means light basically stops at this condition, which sounds a little counterintuitive, but that's what this dispersion relation says. So I want to explain why this is actually happening. From a physical explanation. So first, why light is slow? Why surface plasmons are slower than the free space light? So in order to understand in order to understand that, what we can do is we can actually calculate the energy flow along the propagation direction of the surface plasmons. And as we know, the energy flow along x direction can be calculated by using pointing vector, right? Pointing vector is energy flow. So pointing vector along x direction is E cross H x, right? So this is just the definition. And then we know that this is just a TM mode, so only has y component. H only has y component. So that if you do E cross H, this is nothing but minus EG HY. And then EG and HY, you can calculate EG from HY, right? There's no problem doing that because there's a, you have a Maxwell's relations. Where is it? Here. So if you have HY, if you have HY, you can obtain EG from it, right? So there's no problem doing that. Now, if you do so, your dispersion, your pointing vector along x direction can be summarized into this equation. And then this one, of course, is positive. And if you look at this equation, beta is also positive, omega positive, epsilon 0 positive. But epsilon here, the relative permittivity, can have different signs, right? So in the metal, epsilon m is negative, right? And in the dielectric, epsilon d is positive, as I said, so that the power flow, even though it's the same mode, the power flow inside the metal try to go backward, whereas the power flow of the dielectric material, in the dielectric material tends to go forward, right? That's what this relation says. So that, of course, the forward directional power flow is higher than the backward directional power flow. So that overall, this one goes forward, but it's slow, right? Its energy transfer is much, much slower than the regular wave, where all the wave tends to go forward, right? So this is kind of a physical explanation why surface plasmons are slower than the free waves. And then when omega goes to 0, I said, the surface plasmon tends to very similar to the free wave. And then the reason is when omega goes to 0, then from this equation, epsilon m, the imaginary, the permittivity of metal tends to diverge, right? Because omega goes to 0, this one tends to diverge, right? So it has basically infinitely large epsilon, so that wave cannot penetrate into the metal. It's just metal becomes almost like a PEC in this case. Okay, so that it's like the wave is not, so you have just PEC and a dielectric material on top. So in this case, the wave is basically very weakly bound to the metallic interface. You can, and then you can actually deduce this property by rigorously calculating these relations. So what you need to know is you have to know this gamma 1, and I'm sorry, I guess this one is gamma 1 and this one is gamma 2, right? So the decay length of decay constant of gamma in the metal and in the dielectric, and if you actually calculate it as epsilon m goes to infinity, gamma 1, the decay constant in metal, also diverges, so that decay length becomes infinitesimally short, and then decay constant of decay rate of gamma 2 approaches to 0, so that its confinement along z direction becomes very, very weak. And as a result, beta, which defines like this, is actually approaches to, so this one can be negligible, so that beta approaches to free space light, right? So that's why when omega goes to 0, your surface plasmon becomes almost like a free wave. And we call this as a weakly bound mode. Okay, and SPP, surface plasmon, behaves like free waves. And on the opposite end, when omega approaches to omega surface plasmon, and omega surface plasmon is surface plasmon frequency is 1 over epsilon d, and in this condition, epsilon m is equal to minus epsilon d. Okay, if you calculate this, this is the condition. And in this condition, interestingly, if you calculate the pointing vector, as I said, pointing vector can be written like this. And because epsilon m and epsilon d have exactly same magnitude, but only have different sign, so that at this condition, the power flow in the metal and power flow in the dielectric are exactly same, but on the opposite direction, right? Because epsilon m and epsilon d are basically the same, exactly same. So, so the power flow also exactly the same, but have opposite direction. So they basically cancel each other out, so that the wave cannot propagate to any direction, because it's, this one wants to go this way in terms of energy. This one wants to go that way, so it doesn't go anyway. doesn't go anywhere. So for lossless material at this frequency, when omega approaches to surface plasmon frequency, we can achieve zero energy velocity or zero group velocity. Okay, and in this condition, if you look at the beta, which is defined, this is the dispersion relation. And as I said, epsilon m is equal to minus epsilon d. So denominator becomes zero so that beta diverges, right? So you have like infinitely long beta, which means infinitesimally small wavelength, which means extreme confinement, like infinitely strong confinement. Right. So if you compare bulk and surface plasmon resonance, like as I said, bulk plasmon resonance occurs when epsilon m becomes zero. So epsilon m in our case is like defined p, like this, right? So when epsilon m becomes zero, then this the bulk plasmon resonance occurs, and then bulk plasma frequency is defined like this, okay, as an omega p. And now when we have a surface plasmon, like the interface between epsilon d and epsilon m, then the resonance condition, the surface resonance condition changes to this. Okay, and to me this looks reasonable if you compare. So if you compare like bulk plasmon case, it's metal everywhere, right? So basically this condition is that your permittivity is zero. And here in this case, we have surface. So epsilon m plus epsilon d is kind of an average permittivity of this surface, right? And if this becomes zero, then surface plasmon resonance occurs. Okay, so in a sense, it's reasonable. And then the frequency of surface plasmon resonance is lower than the actual plasma frequency because all you need to do is you apply this equation to here to obtain surface plasma condition. Okay, so the reason why I bring up this comparison is because this type of thinking, like this type of like hand wavy argument, becomes useful when you try to, for instance, estimate the resonance frequency of localized metals. For instance, let's say you have a metal here, metallic ball, and here's the dielectric. Okay. In this case, if somebody say the resonance condition is epsilon m plus some factor multiplied by epsilon d equals zero, then what do you think about this factor? Do you think this factor x is going to be larger than 1 or smaller than 1 based on the geometry? What would you say? Can you type in? Like somebody asks you, what's the resonance frequency of this metallic ball? What's the condition for the resonance? And then if the condition for the resonance can be written like this, then this factor x here in front of epsilon d, is that larger than 1 or equal to 1 or smaller than 1? How would you say? Like what can anyone type in your guess? Larger. Thanks, Thomas. Yeah, that is true, right? So why larger? Because as you can see here, there are more dielectric materials than metal compared to the other two cases, right? So in first case, it's bulk plasmon, it's bulk metal. There's no dielectric at all. And in this case, we have a line interface. so that there's half dielectric, half metal. And in this case, metal, the interface forms a closed volume. And here, of course, there's more dielectric component than the metal. So X becomes larger than 1. So this type of a hand-wavy argument is sometimes very useful to estimate, what is going on. So similarly, omega p, like let's say if you call this resonance frequency as omega resonance, this omega resonance must be lower than even omega surface plasmon. And omega surface plasmon was lower than omega p, right? So, you can see how things are going here. Okay, now we want to talk about metal with damping. So as I said, if the metal doesn't have any damping, which means there's no imaginary part of permittivity, then its dispersion relation gives you infinitely long propagation constant at the omega sp and 0 group velocity and so on. So can we still have beta goes to infinity when imaginary permittivity is non-zero? And as I showed you earlier in our previous lecture, it's not the case. If we introduce gamma, which is decay constant, which is a material loss, material loss. You see here the maximum achievable beta is limited to a finite number, right? And also this blue line, which gives you the imaginary part of k vector, also increases as you go to, as your omega approaches to omega sp. So it's going this way. The propagation distance is also finite and decreases as omega goes to omega sp. So what is propagation distance? So you have k or beta, the propagation constant, the real, so and then it's acting this way, e to the I beta x, and x is propagation direction. So if you divide beta into real part and imaginary part, that becomes e to the real beta x plus I imaginary beta x, right? And then this is e to the I real beta x minus imaginary beta x. So imaginary beta gives you just a decay factor, whereas real beta, due to this I in front, gives you oscillating component, right? So the second part gives you decaying component. So here the propagation distance is defined as 1 over imaginary beta, right? Because that's, if you plug in 1 over imaginary beta, that gives you the condition where your electromagnetic field decays to 1 over E. So because imaginary part here, imaginary beta increases, as you approach to omega sp, your propagation distance decreases, right? So there is a trade-off. As you're approaching to omega sp, or the other way around. So as you're approaching to omega sp, you have larger real part of beta, which means higher confinement. But at the same time, your mode becomes more lossy so that its propagation length also decreases, or vice versa. If you go to a omega far away from omega sp, then of course you have almost negligible loss. But at the same time, the confinement factor is also not too high. So there is a trade-off between propagation length and the confinement factor. And then I'll talk about some ways to kind of overcome this trade-off relation probably after our midterm exam. But anyway, for now, you can understand the propagation length and the confinement are in the trade-off relation. Yeah, and this is a surface plasmons at a real material, real silver interface. So you can see here for the silver air interface and silver silica interface, you can see, this line is of course light line, and this line is surface plasmon. And you can see the surface plasmons have still a finite K vector and going back and forth like that. So it's basically showing the same behavior of this red curve. Okay. And if you actually look at the number here, at lambda 0 of 450 nanometer. So lambda 0 of 450 nanometer is somewhere around here. Okay. So in this case, omega is close to omega SP. In this case, you can see 1 over gamma. 1 over gamma is how much, so the field confinement factor along z direction. Okay, so 1 over gamma is 180 nanometers. So it's much smaller than lambda, right? So the field is tightly confined at the interface. But the propagation length is 16 microns. It's very short. And if you go to a lower frequency, much lower frequency, like or much longer wavelengths, somewhere around here, okay, then wavelength is 1.5 micrometer. And the confinement factor, I mean, the vertical confinement is now 2.6 micron. So compared to the wavelengths, this one is much larger. So it's like very weakly confined, right? And also, if you look at the propagation length, it's much longer than this case, right? Even though you normalize things by lambda, still this is like 2 orders of larger than this case. So here the loss is smaller, but confinement is also low. And here in the upper case, high confinement, but high loss. It's always trade-off. And finally, we have like all the surface plasmon properties of all real materials: silver, gold, copper, and then in this plot, what we see here, this is the propagation constant as we saw. So these are just the dispersion relations, and here L is the propagation length. And as I said earlier, if you look at this, as the wave approaches to surface plasma frequency, the propagation length becomes shorter and shorter, right? Becomes significantly shorter. And also here too, the propagation length becomes significantly shorter as it approaches to the surface plasma frequency. And here, if you look at this, this is a log scale. So it's going rapidly shorter, and also the same here. And another thing that you can notice is that in case of silver, you can get relatively high K vector compared to the free space light, right, at the same frequency. But for gold and copper, the deviation of a surface plasmon dispersion from a free space light is not that large, right? And this is because material loss of gold and copper is relatively larger than the silver, so that the deviation is actually becomes lower. And Thomas asks, which gamma is considered, the dielectric or metal one? I guess this question was about this. Yes. Oh yeah, it's dielectric. So we do care about the dielectric field confinement, because it's kind of difficult to kind of use the electromagnetic field confined in metallic region. So when we say vertical confinement, we always talk about the confinement in the dielectric region. That's a good question.